All right, one more example of integration by substitution, and we have to make sure that we get an example in here that includes using a substitution to perform integration when we have limits on our integral. So this is a definite integral. I can still evaluate it using substitution. And there's actually two ways you can go about this, and we have to know both techniques because they'll both get tested on the AP test. So remember we said that to make our u substitution, we like to think of a u that we can use so that whatever u's derivative is a factor in our integrand. So if I think about this integral, I think of that as tangent x times secant squared of x. And for me, that hope you get to the point where it's easier for you to see. So I'm going to choose u to equal tangent x, because then my du is secant squared x dx. And I'm happy because my du is one of the factors in the integral. So when I isolate my dx, I'm going to write du over secant squared of x is equal to dx. Now when I rewrite my integral, the secant squared that's there is going to cancel with the secant squared in my dx expression. So here's the thing. I'm about to take this integral that's been written in terms of x with a dx in it. My integrand is a function of x, and these limits here are x limits. And I want to rewrite it so it uses only the variable u. I have to make sure I don't leave x limits, these guys, on a u integral. So I have two ways that I can go. I'm going to show you both ways because, like I said, we have to know them both. I'm going to do this problem once where I'm going to avoid that problem of x limits on a u integral by leaving my limits off. Will I have any u's involved? And bringing them back later after I rewrite my answer in terms of x. So that's what I'm going to do here. I'm going to write this as the integral. I'm going to leave the limits off. I'm going to write tangent x. I'm going to write secant squared of x. And I'm going to write dx. And now I'm going to rewrite that integral, and instead of tangent x, I'm going to write u. Secant squared of x, I'm going to leave there for a second. You can probably see what's about to happen. Instead of dx, I'm going to write du over secant squared of x. And now I notice, thank goodness, it's what I needed to have happen. This secant squared of x and this secant squared of x are going to cancel. And my final integral, notice I haven't actually found an antiderivative yet, but my integral now has u and du. Everything else canceled out. I have no x's left in my u integral. And it's really easy to find an antiderivative for u. That's going to be u squared over 2. So 1/2 u squared. I could write plus a constant, because right now my integral looks like it's an indefinite integral. But look, now that I'm going to go back and replace my u with tangent x. This is going to be 1/2 tangent of x, all getting squared. Now I can put my limits back on. This is an antiderivative in terms of x. I'm going to put my limits back on. I'm going to evaluate that from 0 to pi over 3. So that's going to be 1/2 tangent of pi over 3 is radical 3 squared minus 1/2 tangent of 0 is 0 squared. And we get 1/2 times radical 3 squared is 3 times 3. This is minus 0, and my answer is 3 over 2. That's my final answer. That's correct. You would get full credit for that on the AP test. So this was the multiple choice section. Of course, this is going to be one of the answer choices. I'm going to do this same problem a slightly different way and show that I get the same answers. But again, you need to know both techniques. All right, I'm going to do the same problem again. I'm going to make the same substitution. U is going to equal tangent of x du over secant squared of x is equal to dx. That part's all the same as before. I'm going to do one extra piece of work up front. It's going to make my problem finish faster at the end. And that's instead of leaving my limits off and finishing the whole problem, getting back to x's, and then putting back my limits, I'm going to update my limits so that they become u limits. So look at this. I wrote u equals tangent of x. Remember that these limits that are on my integral are x values. So I can find the corresponding u values by sort of running them through this little function that I wrote. So my new lower limit is going to be u equals tangent of 0. Well, that equals 0. So this is lower limit is going to be 0. My upper limit, u equals tangent of pi over 3. So that's radical 3. And that's going to be my new upper limit. These now are u limits, and I'm going to be able to write my whole integral in terms of u. So this is going to be the integral from, my new lower limit is 0. It happens to be the same as my old lower limit, but that's just a coincidence. My new upper limit is square root of 3. Instead of tangent x, I'm going to write u. Instead of secant, I'm going to write secant squared x. And instead of dx, I'm going to write du over secant squared of x. Maybe you're starting to notice that these are going to cancel out, and you can write this in fewer steps. That's fine. But now I have a new integral. It has only u's. It has u limits. And this is u du. Well, the antiderivative of u is 1/2 u squared. And I'm going to evaluate that from 0 to radical 3. In this case, I'm not going to bother changing back to x limits or changing back to the letter x because I have an expression that I'm going to be able to evaluate and get one final answer. So this is going to be 1/2 of radical 3 squared. So 1/2 radical 3 squared minus 1/2 of 0 squared. It's going to be 3 over 2 minus 0. I'll get the same answer that I got before. So this is this idea of updating your limits so that they're u limits. It's going to follow us into chapter 7. It's definitely going to be tested on the AP test, so watch out for it. And these two methods of simplifying or integrating with a u substitution, you're going to need to know.